The first question that we are going to see is the electric field due to an electric dipole. Which point we are considering? The axial point we are going to consider. Okay. So let's consider here an electric dipole, right? Let's say this is plus Q, this is minus Q. This is the center of the dipole. The length of the dipole, let's say we are taking it as 2a. Okay. From the center to both the charges, let's take the distance is a. We consider a point along the axial line. This is the point P, which is along the axial line. Let's say the distance from the center of the dipole to the point P is, let's say, R. Okay. So now at this point, at point P, what is the net electric field is what we are going to find. We know that the electric field at the point P due to plus Q charge, it will be away from it, correct? Because due to isolated point charges, electric fields will be away from it. We can write it as what? E plus Q. Due to negative charge, it will be towards it. We can mark it as what? E minus Q. All right. So we can write the equation for the positive and the electric field due to both the charges. We may write it as E plus Q if you are writing how much that will be equal to. We can write it as 1 by 4 pi epsilon 0 Q divided by magnitude of the charge divided by the distance from the charge plus Q to that we need to find, right? What will be that distance from plus Q to this if you are taking? It will be what? R minus A it will be coming, correct? So we have to take like R minus A the whole square, right? And in what direction actually this electric field is? We know that the electric dipole moment of an electric dipole is directed from where to where? It is directed from minus Q to plus Q, right? And the direction of E plus Q and the dipole moment P, they are the same, correct? They are parallel to each other. So I'm going to write in terms of unit vector of dipole, a unit vector in the direction of dipole moment, I'm marking as P cap, okay, and E plus Q, like this we can write. And the electric field due to minus Q, we can write it as what? 1 by 4 pi epsilon 0 Q divided by the distance from minus Q to P. What will that be? It is R plus A the whole square it will be, right? And the direction of it, you see, it is in the opposite direction of dipole moment. So I'm taking it as what? Minus P cap, correct? And the net electric field, you can write as what? The sum of these two, E plus Q, correct? Plus E minus Q, you can write. Vectorially, we have to add these two. Correct. And what is that you're going to get? We can write that will be equal to vector E. I'm writing on the right hand side now. Vector E, what will that be equal to? 1 by 4 pi epsilon 0, right? Q divided by R minus A the whole square P cap plus 1 by 4 pi epsilon 0 Q by R plus A the whole square minus P cap. Correct. So common things, let's take it outside. So you get 1 by 4 pi epsilon 0. Q is also there, right? So Q I'm taking here, right? And 1 by R minus A the whole square. Here this minus is also there. I'm plus positive plus minus, it will become minus into 1 by R plus A the whole square. P cap also I took it outside. So this becomes Q by 4 pi epsilon 0, correct? Into cross multiplying what will happen? R plus A whole square, what it is? R square plus A square plus 2AR minus R square plus A square minus 2AR divided by this is now like what? R plus A into R minus A the whole square, right? Into P cap. So this will be giving you what? Q divided by 4 pi epsilon 0. If you expand this, what will happen? R square plus A square plus 2AR minus R square minus A square plus 2AR divided by the terms in bracket A plus B into A minus B form. So you can expand it to R square minus A square the whole square, correct? Into P cap. So what will happen? R square cancels, A square cancel. 2AR plus 2AR, it is nothing but 4AR. So you'll get Q by 4 pi epsilon 0. 4AR divided by R square minus A square the whole square P cap, right? We know the dipole moment is nothing but what? 2QA. So you can write this equation as what? 1 by 4 pi epsilon 0. See, 4AR, you have to write it as what? 2 into 2AR, right? So 2A into Q is nothing but what? Dipole moment P, magnitude of the dipole moment. So you can write this as 2PR divided by R square minus A square the whole square P. All right. Or you can finally write this relation, this electric field relation, we can write in this form. Vector E, yeah, I'll write it here. Final relation vector E that is equal to what? 1 by 4 pi epsilon 0. 2p into p cap. You can write it as what vector p into r divided by what r square minus a square the whole square. And that's the relation for what the electric field due to dipole along the axial line. If in this case, if you are taking, if a is very much less than r, if you are taking, okay, it's a short dipole if you are considering, okay, in the case of short dipole, what will happen? R square minus a square, you can approximate to r square, right? So this equation become what 1 by 4 pi epsilon 0. E will be equal to what? Vector E is equal to 1 by 4 pi epsilon 0. 2p r divided by r to the power 4 will come, which is nothing but 2 vector p divided by r cube. So for short dipoles like this also, we can write the relation. All right, now the second question that we are going to see is the electric field due to the electric dipole only, but the equatorial point we are going to consider. Okay, so let's draw the diagram for this. What is it? We have the dipole, let's say this is the plus q and this is the minus q. They are separated by what distance? We'll take it as 2a only. This is the center of this. And from here, let's consider a point P, okay, where we are going to find the electric field due to the dipole, right? So due to plus q charge again, the electric field will be away from this. You can mark this as E plus q, correct? Due to this minus q, we know the electric field will be towards that, right? Only due to that, if you are taking at the point P, electric field will be E minus q towards it, we can write, correct? So now, if you are taking these distances, we know this distance is A. Let's say this distance from the center of the dipole to the point P is R. So this distance, obviously, it is nothing but what R square plus a root over R square plus A square. By Pythagoras theorem, easily you can write. Correct. So here, what I'm going to do, see here, this angle, if you are going to take it as theta, I'm going to resolve this E plus Q into the two components. Which will those be? This will be E plus Q. If this is theta, this angle will also be theta, correct? So this will be E plus Q cos theta, you can write, and this will be E plus Q sin theta, correct? The same way, E minus Q also you resolve into the two components. This will be E minus Q cos theta, and this will be obviously what? E minus Q sin theta, basically, correct? E minus Q sin theta. So what will happen basically? Here, if suppose these two magnitudes, if you are going to write, what will that be? E plus Q, if you write, correct? E plus Q, what will that be equal to? 1 by 4 pi epsilon 0 q divided by what is the distance here? Root over r square plus a square. So that square you have to write in the denominator here. So r square plus a square. In what direction this is? This is away from plus q. You can actually write. At the same point, E minus q, electric field due to minus q charge. How much that will be? 1 by 4 pi epsilon 0 q by magnitude we are taking now. Q divided by distance is again same in this case also. So r square plus a square only, it will be towards what? Towards minus q. Correct? But at this point, you have to note one very important thing. Both these two, E plus Q and E minus Q, magnitude wise, they are same. So when you come back to the diagram here at the point where we have resolved the magnitudes of the electric field, E plus Q sin theta and E minus Q sin theta, they will cancel off. Why? Because they are E plus Q and E minus Q, magnitude wise, they are same. And these angles involved are also same. So they cancel off. So the net electric field at the point P, if you are taking, it will be nothing but it magnitude wise, this is actually how much it will be. E plus Q cos theta, correct? E plus Q cos theta plus E minus Q cos theta, it will become, correct? Magnitude wise, if you are taking, right? And in what direction it is? We know dipole moment is from minus Q to plus Q. This is actually in the opposite direction of that. So minus P cap, we have to write here. Right. And we have to note that E plus Q cos theta and E minus Q cos theta, they are magnitude wise same. So you can write it as what? Twice E plus Q cos theta, right? Into minus P cap. This is what the dipole moment, the resultant electric field there will be getting. Correct. So we will substitute now E plus Q. We have the value. Let's substitute here now. So we'll get actually EP if we are taking. It is nothing but 2 into what is E plus Q? 1 by 4 pi epsilon 0 q divided by r square plus a square. Correct. What is cos theta here? Cos theta is adjacent by hypotenuse. Adjacent is nothing but a divided by root over r square plus a square into minus p cap is what you'll be getting. So this 2qa, you can write it as what? Dipole moment P, and this relation become 1 by 4 pi epsilon 0 vector, P divided by if you see here, x to the power 1 into x to the power half. Root is nothing but what? Half. Root x, we can write it as equal to what? X to the power half. Correct. So this will be equal to what? X to the power 3 by 2, we can write. So this obviously r square plus a square whole to the power 3 by 2 into minus p cap. Correct. Or vectorially, if I'm writing, I can write this as in vector terms only, because in terms of uh, direction also we have specified there, correct? So the resultant electric field at the point P, what does that be equal to? 1 by 4 pi epsilon 0. P cap is nothing but what? Vector P, right? Minus is also there, divided by r square plus a square whole to the power 3 by 2. And this is the electric field due to the dipole at an equatorial point. At the same time, if in the case of short dipoles, if you are taking, what is the case of short dipole? A is very much less than R. In that case, what will happen? R square plus A square. You can approximate to what? R square plus A square. You can approximate to what? R square, right? So R square whole to the power 3 by 2 means it will come R cube. So you can write vector P. EP, that is equal to what? 1 by 4 pi epsilon 0 minus vector P divided by R cube. This is in the case of what? Short dipoles. All right, the next question. The electric field due to uniformly charged spherical shell, the application of Gauss law. Okay. So we apply the Gauss law and we find the electric field due to a uniformly charged spherical shell at three different points, which are all outside, on the surface, and inside. Okay, let's do this one. Let's consider here a spherical shell. This is uniformly charged, suppose. Let's say it is uniformly positively charged. The total charge on it is suppose Q, and let's take maybe the surface charge density is sigma. Let's say the radius is capital R. Okay, first let's consider the electric field due to it. Okay, outside the spherical shell, what will be the electric field? Let's consider. Okay, so for that, let's consider a point P, let's say, which is outside the spherical shell. So what we have to do? How do you apply Gauss law? First point is you consider a symmetrical Gaussian surface to make the process easy. Second thing is we need to find the total flux through the Gaussian surface. Last thing is to apply the Gauss law basically, correct? Which is nothing but the total flux is equal to Q enclosed divided by epsilon naught. So let's consider here in this case, which will be the easiest or the symmetrical Gaussian surface. It will be nothing but a concentric spherical surface on. So let's consider here a concentric spherical surface like this. Okay, so here we need to find, so the Gaussian surface we found. What is the next point actually? To find the flux through the Gaussian surface. Okay, how to find the flux through the Gaussian surface? Let's consider a small surface here. Okay, a small section we are taking whose area, let's say ds, right? Now we know due to this spherical shell, which is uniformly charged, the electric field at that point, it will be radially outwards, correct? So the flux through that small section, if I'm going to take d phi, right? The flux through that small surface, how much that will be equal to E dot ds when you are taking, right? Area as a vector quantity only. Outward normal, we take it as the direction of area vector here, and we see that E and ds will be in the same direction. So you can write this as what? Just E ds you can write. So the total flux through the Gaussian surface, you can find it by integrating this E ds for the complete Gaussian surface. Since actually this is a symmetrical case we are seeing, okay, where both the spheres are concentric, electric field at any point on the Gaussian surface, if you are taking, it will be constant only. So you can take it outside the integration, you'll be getting E into integral ds you'll be getting. Okay, so E into integral ds is nothing but what? The total surface area, correct? The total surface area of that Gaussian surface. We are taking that this distance is small r, suppose. So this will be obviously giving you what? 4 pi r square, because it is a spherical surface. So 4 pi r square we can write. All right. So here what we do next, we apply Gauss law, right? What is Gauss law? We know that the total flux through any closed surface is nothing but Q enclosed divided by epsilon naught. So here we have this. This is also equal to what is the charge enclosed? It is nothing but what? Q only. So you can write Q by epsilon naught, right? So we have these two. right? We have phi is equal to E into 4 pi r square. Also, we have Q enclosed by epsilon naught. So we can write what E into 4 pi r square, that is equal to what Q by epsilon naught, or E is equal to what 1 by 4 pi epsilon naught Q divided by r square, right? This is the magnitude of electric field. Obviously, electric field is radially outwards, so you can write vectorially if you want. You can write 1 by 4 pi epsilon 0 Q divided by r square r cap, radially outwards. This is how we will be writing. If you want, you can write this equation also in terms of what the surface charge density also. E is equal to what you can write 1 by 4 pi epsilon 0. See, Q you can write it as equal to what sigma into 4 pi capital R square you can write divided by R square. So what will happen? 4 pi get cancelled off. What you're going to get? Sigma into capital R square divided by epsilon 0 small r square. So in this way also, if R cap, if you are right, like this also, we can write what the electric field in this case. All right. Okay. So that's how we find the electric field due to what? A uniformly charged spherical shell outside, a point outside we are seeing. See, at the second case here, it is on the surface if you are taking, correct? On the surface of the spherical shell. In this case, very simple thing. What you have to do, R is equal to capital R, you will be considering. This Gaussian surface that you're considering will be on the surface of this only you'll be taking. So obviously what will happen, you can write the electric field, right? What will that be equal to 1 by 4 pi epsilon 0. Just replace small r by what? Capital R. Q divided by capital R square, it will be coming. It will be obviously radially outwards only you can write. Or you can write the second relation, you can write vector E. What will that be equal to? See, R square, small r also, capital R only. So R square will get cancelled. You'll be getting what? 1 by 4 pi epsilon 0. Sorry, in terms of sigma, we are doing now. Sigma by epsilon 0 r cap. Okay, like this we can write. The third point, what is that we have to see? A point inside. Okay, the point we are considering is inside. So here, this is actually a simplest case. What is simple case actually? What is the thing? They have the spherical shell we are seeing. To apply Gauss law, to find the electric field at a point P inside, what you have to do, you have to consider the Gaussian surface inside. So here in this case, if you are seeing, what will happen? Obviously, the Q enclosed will become equal to what? 0 only, right? So Q enclosed is 0. So obviously the total flux become equal to 0. So easily you can tell what the electric field inside will be what? 0, you can actually tell, right? So this is how we find the electric field due to what? A uniformly charged spherical shell as an application of Gauss law at different points. All right, the next question, the next important question, which one it is? The potential due to point charge. So here let's consider a charge Q. Okay, we are going to find the potential due to this at a point P, which is at a distance r from the charge. Okay, we have to consider the basic definition of electrostatic potential, right? So what is electrostatic potential at a point? It is the work done in moving a unit positive charge from infinity to that point. Very simple. So if we are considering in that sense, we are moving actually a unit positive charge from infinity to the point P. What will be the work done for that? That will be the potential at the point P. For that, let's consider an intermediate point, let's say P dash, which is at a distance x from the charge Q, right? So when the charge is at, when this unit positive charge is at the point P dash, it will experience a force. In what direction? Let's say if the charge Q, the source charge is also positive, so this will experience a force outward. So to balance this, you want to move it to this point P, okay, without accelerations. You want to apply a minimum force that is equal to minus F in the opposite direction of what? F. All right. So if suppose against this repulsion, you're moving this through a distance, a displacement, suppose dx, the small amount of work done for that, how much that will be equal to, you can write it as minus F dot dx, we can actually write. Or you can write it as what? Minus F dx, correct? Because minus F and dx are in the same direction. Okay. Now, how much is this repulsive force? Since it is at a distance x, you can write this force is as what? By Coulomb's law, 1 by 4 pi epsilon 0. What are the charges? Q into the other charge is 1 only, correct? One unit positive charge only, divided by x square, into dx, correct? So here we can write this will become equal to what? This will be equal to minus 1 by 4 pi epsilon 0 q by x square dx. This is basically the work done for this, right? So the total amount of work done, if you are moving it from infinity to the point P, the total amount of work, how do you find? You integrate this small amount of work, correct? From where to where you have to integrate from infinity to R. So what will this be? You integrate it from infinity to R. This minus 1 by 4 pi epsilon 0 q divided by x square dx. All right. So here this terms that are constant, you can take it outside. That is q 4 pi epsilon 0 negative all, you can take it outside. Minus q divided by 4 pi epsilon 0 integral infinity to r 1 by x square dx it will become. Correct. So that will become equal to what? Minus q divided by 4 pi epsilon 0. Integral 1 by x square. 1 by x square is nothing but what? X to the power minus 2 from infinity to r dx. And what will that be? Equal to minus q divided by 4 pi epsilon 0. Integral x to the power n. What is that equal to? Integral x to the power n dx is nothing but x to the power n plus 1 plus c. Okay, with the limit you are doing, so no need to consider this constant that will be coming. So x to the power minus 2 plus 1 divided by minus 2 plus 1 with the limit from where to where? Infinity to r. So you get minus q divided by 4 pi epsilon 0 into x to the power minus 2 plus 1 is x to the power minus 1 only, correct? So x to the power minus 1 divided by minus 1 with the limit from infinity to r. So this negative and this negative will get cancelled. So you'll be getting q divided by 4 pi epsilon 0 into x to the power minus 1 means what? 1 by x only, correct? 1 by x only with the limit from where to where? Infinity to r. So you'll be getting q divided by 4 pi epsilon 0 into applying the limit, what you get? 1 by r minus 1 by infinity. 1 by infinity is approximately, it's very small, we can take it as 0. So you will be getting, this will be 1 by r, right? So obvious, very clearly we got this relation. This is equal to what? 1 by 4 pi epsilon 0 q by r you got, right? And this work is what we call it as the potential at that point, because what we have found the work, it is a work done in moving unit positive charge from infinity to that point P, and that is nothing but the potential at the point P. So we can write this is equal to what? The potential. Okay, so the potential due to point charge at a distance r from it, how much is equal to 1 by 4 pi epsilon 0 q by r. All right, let's go for the next question. Right, the next question, it is the potential due to electric dipole. Okay, so let's see here. See, while drawing this diagram, you should be careful a bit here. Okay, so the dipole, when we are drawing, okay, you have to draw it like this. So we have the negative charge, positive and the negative charge when you are drawing. See, I'm drawing plus q here and minus q here. Okay, they are connected by this. I mean, like the distance between them, let's take it as what? A and A. Right. Now see here, I'm considering an oblique point. A point P I'm going to consider, okay, which is more aligned to what? This positive charge, so that this derivation will be easier. Okay. So be careful on this part. Okay. So let's consider this point P is at a distance R from the center of the dipole. Okay. Right. So now, if we are seeing, see, from the minus q charge, this point P is at a distance, as you can see, like this, and this point will be at a certain distance, like this. We can actually write, correct? Okay. So now, in this case, when you are taking, we are going to make an approximation on the distance. We are considering short dipole only in this case. Okay, we consider only short dipole where r is very much greater than a. And when you consider r is very much greater than a, what you can do? We can make a slight approximation. And what approximation is it? See, on the side of minus q, if I'm taking this central line that I've drawn, I extend it a bit, okay, and I put a perpendicular from minus q to that line, okay, so that this angle is how much? 90-degree you'll be getting. Okay, so here if you are taking, okay, this angle, if you are taking as theta, this angle will also be theta, right? And in that, if you are taking cos theta, what you are going to get? Cos theta, if you take, cos theta will be equal to this distance that you'll be getting, correct? Let's mark it as x if you are taking that x divided by the hypotenuse, which is something but what? A. So you get x equal to what? A cos theta is what you're going to get here, correct? X is equal to A cos theta will be getting. At the same time, what you can do on the side of plus q, from plus q, if you put down a perpendicular onto that line connecting the center of the dipole to that point P, this angle will also be what? 90 degree you'll be getting. So the same way there, this distance, let's say if you mark it as y, if you are going to mark, okay, in the second triangle that I've drawn, if you mark cos theta, what would that be equal to? Cos theta is adjacent, which is nothing but y by a. You can write. Hypotenuse is a, obviously. So y is again equal to what? A cos theta. We can actually write. Okay. So the point is, if I mark suppose these 2 points as a and b, to get the distance AP, this you can approximately, you can write it as equal to what? R plus X, which is nothing but what? A cos theta, we can actually write. And the BP, you can approximately write it as equal to what? R minus A cos theta. Okay. So this is the crux of this problem. So let's consider here now the net potential at the point P, right? Potential at the point P will be nothing but equal to what? Potential due to the positive charge and potential due to what? Negative charge. Potential is a scalar quantity. We just have to add it scalar, just add the magnitudes, right? So here what is the potential is actually a scalar quantity. Scalar addition is enough. So potential due to point positive charge, if you are going to take, what does that be? 1 by 4 pi epsilon 0. Potential due to point charge or already previously we took, right? Q divided by what is that? That distance you can take it as what? R minus A cos theta. You can actually take, correct? Plus 1 by 4 pi epsilon 0. Minus Q, the charge is negative here. So minus Q divided by distance is what? R plus A cos theta, correct? Right? So like this you'll get. So here, what you can do now, things that are common, you can take it outside, right? So you'll be getting 1 by 4 pi epsilon 0 or q divided by 4 pi epsilon 0, you take it outside into 1 by r minus a cos theta. This plus or minus, minus it will become 1 by r plus a cos theta, it will be given. Correct. So how do you simplify this? Just cross multiplication is enough. So what is that? You'll be getting q divided by 4 pi epsilon 0 into cross multiplying, you get what? R plus a cos theta minus of, this means what? R plus, correct? Minus of, a minus become plus, R plus a cos theta divided by, this is like a plus b into a minus b only. So again, we can do what? R square minus a square cos square theta. We can actually write in this case. All right. So what will happen here? We get actually the potential at the point P, Vp. What is that equal to now? Q divided by 4 pi epsilon 0 into, see, R plus a cos theta. R and R will get cancelled here. So you'll be getting what? 2a cos theta divided by R square minus a square cos square theta is what you'll be getting here. Correct? So here what will happen? 2qa is nothing but what? P. So you'll be getting 1 by 4 pi epsilon 0 p cos theta divided by r square minus a square cos square theta is what you'll be getting. Correct? So here obviously we have taken the consideration that r is very much greater than a. So r square, this a square cos square theta you can neglect in comparison with r square. So you'll be getting the potential at the point P. What would that be? 1 by 4 pi epsilon 0 p cos theta divided by r square. And that is the potential due to what? The electric dipole. The next question, the cells in parallel. Let's do it. Let's consider here two cells, right? They are supposed connected in parallel. Very clear, correct? Let's say the EMFs are epsilon 1, epsilon 2, internal resistances are R1 and R2. Okay. Let's say a total of I current actually passes through the complete circuit, of which I1 passes through the top branch, I2 passes through the lower branch. We know the EMF. I mean, EMF, the terminal potential relation, we know how to write. What is that? V is equal to what? Epsilon minus IR relation we know. Since actually the two cells are in parallel, potential across both will be what? Same. So if I'm writing the potential across the top, V, if I'm going to write, that will be equal to what? Epsilon 1 minus the current through that is I1 into R1. We can actually write. So from this equation, if I'm going to write the equation for I1, what would that be equal to? Epsilon 1 minus V divided by R1, we can actually write. Where I1, R1 I took to the left hand side, V to the right hand side, and then R1 I took to the right hand side. Same way, if I take the lower cell, if I'm going to take, you can take, you that also we can write V is equal to what? Epsilon 2 minus I2 R2, you can write, which will give you what? I2 is equal to epsilon 2 minus V divided by R2. Very easily we can write. But at the same time, if suppose I'm going to apply uh, the Kirchhoff's current rule, the Kirchhoff's junction rule, I'm going to apply. Okay, at that junction, you can write I is equal to what? I1 plus I2. We can write this, correct? And that will be equal to what? Let's substitute the values here. Epsilon 1 divided by R1 minus V by R1, correct? Plus epsilon 2 by R2 minus V by R2, we can write. Okay, so how do you simplify this one now? We can write this as I'm going to write I is equal to what is that? Epsilon 1 by R1 plus epsilon 2 by R2. I'm taking V common, so you'll be getting V into 1 by R1 plus 1 by R2. I'll get. Okay, so now what I'm going to do, see here, this term that V minus V into 1 by R1 plus 1 by R2, that term I'm going to take it to the left hand side. So you get V into 1 by R1 plus 1 by R2, that is equal to what? Epsilon 1 by R1 plus epsilon 2 by R2 minus I, we can actually write. Okay. So next, see here what I'm going to do. V, that is equal to, see, if you cross multiply this 1 by R1, okay, let's write this one more step. If I cross multiply this, you get what? R1 plus R2 divided by R1 R2, correct? This is equal to epsilon 1 R2 plus epsilon 2 R1 divided by R1 R2 minus I, you'll be getting. Now what I'm going to do, this term that is there in the bracket, I'm going to take it to the right hand side. So you'll be getting what? That is equal to what? Epsilon 1 R2 plus epsilon 2 R1 divided by R1 R2 divided by, I'm going to divide that separately. So you'll be getting R1 plus R2 divided by R1 R2 minus I divided by, this means what? R1 R2 divided by R1 plus R2. That reciprocal I took, reciprocal multiplication I did. So here what will happen? This R1 R2 will get cancelled. You'll be getting equal to what? Epsilon 1 R2 plus epsilon 2 R1 divided by R1 plus R2 minus I into what? R1 R2 divided by R1 plus R2. We can actually write. Okay. So now if we are going to compare this with an equivalent cell, what is an equivalent cell? Here I am considering if these two together behaves like a single cell of EMF epsilon equivalent, internal resistance R equivalent through which I current is passing. For that equivalent cell, we can write what? V is equal to epsilon equivalent minus I into R equivalent. We can actually write. So very clearly, epsilon equivalent is equal to what? When you compare these last two equations, if you are seeing, epsilon equivalent will be equal to what? Epsilon 1 R2 plus epsilon 2 R1 divided by R1 plus R2. All right. And R equivalent, you are going to get what? R1 R2 divided by R1 plus R2. Very clearly, we can actually write this. See, it is easier to write this equation or to keep in mind in one more way if you are writing. See this R equivalent, you can write obviously. See this 1 by R equivalent, you can write it as equal to what? 1 by R1 plus 1 by R2. Okay, very clearly we can write. At the same time, if you divide this epsilon equivalent by with R equivalent, what you are going to get? See, this epsilon 1 R2 plus epsilon 2 R1 divided by R1 plus R2 divided by what? R equivalent is R1 R2 divided by R1 plus R2. So what will happen? This R1 plus R2 will get cancelled off. You get epsilon 1 R2 plus epsilon 2 R1 divided by R1 R2. Or in simple terms, we can write epsilon equivalent by R equivalent. What is that equal to? Epsilon 1 by R1 plus epsilon 2 by R2 we can write. And this is the equivalent EMF of two cells that are connected in parallel. This is how you find it. And R equivalent also, we can find it in this way. See, cells in series also sometimes the question is importantly asked. So let's consider this case also. So here we are having two cells that are taken in series. Let's say the EMFs are epsilon 1, epsilon 2, internal resistances are R1 and R2. Let's say an I current is passing through this. So if we are taking the potential across the first cell, the terminal potential difference, you can write what? Epsilon 1 minus IR1, we can actually write, correct? V1 is equal to what? Epsilon 1 minus IR1. And that across the second one, if you are taking, you can write what? Epsilon 2 minus IR2, we can actually write. And the total potential across both together, okay, across the two together, if you are taking the total potential difference, what you are going to get, it is nothing but V1 plus V2, which you can write it as what, epsilon 1 plus epsilon 2 minus I into what, R1 plus R2. We can write very easily, just adding these two together. Now, if you are considering the equivalent cell here, then whose EMF is epsilon equivalent, internal resistance is R equivalent, I current is passing through. The total terminal potential difference across that, you can write it as what, epsilon equivalent minus I into R equivalent. So if we now compare between these two equations, you get epsilon equivalent, what is that equal to? Epsilon 1 plus epsilon 2, and R equivalent is nothing but what, R1 plus R2. And that's the relation we want in this case. If you want, you can write this for n cells also. N cells, you can write it as what, epsilon 1 plus epsilon 2 plus etc. You add up all those together. Obviously, R equivalent to what will be R1 plus R2 plus etc. You just add up all those internal resistances also. That's how we do what, cells in series. The next question, the Wheatstone bridge balancing condition we are seeing. Let's draw the circuit diagram first and let's analyze, and we'll apply Kirchhoff's laws in that, and we'll get to the balancing condition. So let's consider here a network of four resistors. We know uh, the Wheatstone bridge is nothing but this network of these resistors. Let's say this is R1, this is R2, this is R3, and this is R4. Okay, I would suggest you follow the same marking actually. Okay, otherwise confusion might come. Okay, so let's say this is A, B, C, and D. Okay, between these 2 points A and C, you're connecting a cell. Okay, because of which a certain current I will pass through. Now let's say between B and D, you're connecting a galvanometer who's having a resistance what, capital G. Okay, so this current I at this junction A, if you are seeing, it splits into two. It's split into I1 and I2. Okay. Now this I2 at the junction B, it splits into two. A certain current IG passes through the galvanometer, remaining I4, it will pass through R4. So I4, obviously, you can write it is nothing but I2 minus IG. And this IG and I1 combined together flow through what, I3, through R3. You can write it as this I3, what is that equal to? I1 plus IG, you can write. And this combined together, this circuit is completed. I current flows to the cell also. This is how our circuit is. Okay. So now, basically, we need to apply the Kirchhoff's voltage law for this. Okay. And we apply this for two loops. Okay. First, we apply this for the loop. Which one? A, B, D, A. Okay. A loop we are considering A, B, D, A. And let's apply the Kirchhoff's voltage law. Now, be very clear here. We need to apply this with the sign convention. Otherwise, it will go wrong. Okay. So, if you are going in the direction of current across a resistor, the potential across that potential across that, you have to take it as what, minus IR. Correct. So that's what. So moving from A to B, you are going in the direction of current I2 across a resistor R2. So you can write this as what, minus I2 R2 we can write. Now from B to D, when you're going, A to B we reach. Now B to D, when you're going again in the direction of the current, that is the galvanometer current. So minus Ig into its resistance is nothing but what? G. Correct. Now from D to A, you're going in the opposite direction. So you can write plus I1 R1. This is equal to what you can write? 0. Okay. So now you multiply this by, suppose negative means you get I2 R2 plus IgG minus I1 R1, that is equal to 0. Let's put this as equation number 1. Okay. Now at the same time, let's apply this for the loop, the Kirchhoff's voltage law. Kirchhoff's voltage law, let's apply for the loop BCDB. Okay, BCDB. So now what will happen here, from B to C, when you're going, again you're going in the direction of current only. So minus I4 R4. Correct. From C to D, you're going in the opposite direction. So plus I3 R3 you need to write. Correct. From D to B also, you're going in the opposite direction. So plus IgG, that is equal to what? 0. Now you multiply this by minus, you get I4 R4 minus I3 R3 minus IgG, that is equal to 0. We substitute for I4 and I3 also. What is I4? It is I2 minus IG into R4 minus I3 is what? I1 plus IG into R3. Correct? Minus IgG. This is equal to what? 0. This is our equation number 2. Okay. Now let's apply the balancing condition. Okay. If you consider a balanced Wheatstone bridge, okay, what you can tell in a balanced Wheatstone bridge, basically IG is equal to what? 0. You adjust the values of R1, R2, R3, and R4. And if suppose the Wheatstone bridge is balanced, then the current through the galvanometer is 0. Galvanometer shows null deflection. Then what will happen to our equation number 1? Equation number 1 becomes Ig 0 means I2 R2, right? Minus I1 R1 is equal to 0. Or I2 R2 that is equal to what? I1 R1. Very clear now? So now what will happen to equation number 2? Equation number 2 becomes when Ig is 0, all the terms where Ig is coming, you have to take it as 0. So I2 R4 minus I1 R3, third term is 0 only, equal to 0. Or I2 R4 that is equal to what? I1 R2. This is equation number 4. Okay. So now very clearly what you have to do, equation 3, you divide with equation number 4. So you get what? I2 R2 that is I2 R2 divided by I2 R4 that is equal to what? I1 R1 divided by I1 R2. What will happen? I2 cancels here, I1 on the right hand side. You get R2 by R4 that is equal to what? R1 by R2. Sorry, R3 I guess here. Right? In the equation number 2, this factor we made it wrong. This is R3. Okay, so this is R3 you have to mark here. Okay, so you'll be getting what this R1 and R4 if I interchange their positions, you get okay R2 by R1 that is equal to what? R4 by R3, and this is the condition for balanced Wheatstone bridge. Okay, the balancing condition of a Wheatstone bridge, this is it, R2 by R1 that is equal to R4 by R3. You have to finally check it whether you have got it right or not with this thing. You can see that the resistors, how was it in their order only, the equation also you should be getting. See here R2 by R1 that is equal to R4 by R3, and that's the balancing condition of Wheatstone bridge. All right, here we go for the next question. The expression for conductivity. We are deriving an expression for conductivity in terms of what? Relaxation time. The conductivity sigma and the relaxation time tau. What is the relation? Let's. So for this, let's consider here a conductor, right? So let's say it is having this electrons within it whose number density is n, right? So if let's say the area of cross section of the conductor is A, length is L. So the total number of electrons, free electrons which are ready to move, you can write it as what? N into A into L, where N we have taken as what? The number density. N is the number density of free electrons within that. Number density means what? Number of electrons per unit volume, number per unit volume. So into volume will give you total number. So the total charge that are available to move within the conductor, you can write it as what? NaL into charge of an electron is nothing but what? E. The total charge available now is nothing but NaL into E, where we have done what? Charge of one electron into total number of electrons. So Q we got. So if we are suppose going to find the current, if you apply certain potential difference across this, the current due to that you can write it as equal to what? Q by T, which is nothing but NaLe divided by T. This L by T, you can write it as what? The average velocity with which electron drift inside or the drift velocity. So you can write NaeVd, we can write, where Vd is the drift velocity of electron, we can actually write. So here in this case, if I take A to the left-hand side, you get I by A, which is nothing but what? The current density J, that is nothing but what? NeVd. Okay. So now we have got this J is equal to what? NeVd. What is the relation for drift velocity? Vd is nothing but what? In terms of relaxation time, you can write it's a magnitude if you are writing E by M into tau, correct? This is the drift velocity relation, correct? So this, if we are substituting back in this equation, you get J is equal to what? Ne into E by M into what? Tau. Or you get Ne squared tau by M into E. This is what J. Now we know the Ohm's law, the actual form. What is that equal to? J is equal to what? Sigma E. correct? So now if you compare these two relations, what you're going to get, the conductivity sigma is nothing but what? Ne squared tau by n. And that is our required relation for conductivity in terms of the relaxation time. Sigma and tau, this is how you connect. And that's the relation. Sigma is equal to what? Ne squared tau by n, where n is the number density of electron, E is the charge of the fundamental unit of charge, the basic elementary unit of charge, tau is the relaxation time, m is the mass of electron. Right, going for the next question. Magnetic field due to circular current carrying coil. Okay, we consider an axial point. For this, what we do, we consider a circular current carrying coil, right? So here is that circular coil, suppose, right? We are assuming that the plane of this coil is perpendicular to the plane of the screen, okay? So let's consider here a point P where we are going to find the magnetic field, okay? We are taking this is at a distance x from the center of this, okay? Let's say an I current is passing through this. To find the magnetic field at the point P, what we have to do? We have to apply Biot-Savart law. For that, we have to divide the entire current carrying wire into small section. Let's consider a small section of length what dl at the top of this, right? So now, due to this, at the point P, what is the magnetic field I need to get, right? So let's say that is dB. How much that will be equal to? If this distance is r, you can write mu naught by 4 pi I dl, right? Current through that is I dl is the length of that. Sine, what will this angle be? You need to note that this angle is actually perpendicular because I told you the current carrying wire, the circular wire, its plane is perpendicular to the plane of the screen. So sine 90 divided by what will be r square will be it. Okay. So this will be equal to what? Mu naught by 4 pi. Ideal sine 90 is 1 only divided by what is r here? R is nothing but if you take r is the radius of the circular loop, r is nothing but what? Root over r square plus x square. You can write Pythagoras theorem very easily. So r square means what? R square plus x square. Directly we can actually find it. Correct. But and the direction of this dB, what is the direction of this dB? See, direction of dB is perpendicular to both dl, right, and this r, correct? Because you can write the in vector terms if you are writing the what is that relation? Mu naught by 4 pi I into dl cross r divided by r cube it is, correct? So that means it is perpendicular to, right, dl cross r divided by r cube it will be coming. So this is actually perpendicular. dB is perpendicular to both the DL and R, and it will be coming in this direction if I'm marking dB. Correct? Okay. So if suppose this angle, if you are going to mark it as theta, okay, I'm going to resolve this dB into the two perpendicular components. If this is theta, this is 90 minus theta. This will be theta, obviously, right? This is 90 minus theta, and this you will get as what? Theta. So this you can write it as what? This component dB cos theta. This will be dB sin theta. Very clearly, we can write. All right. So now here is the next very important point. What is that? See, if diametrically opposite, if I consider another element, okay, of same length dl, if you take, due to this, if I consider the magnetic field at this point, in what direction that will be? It will be in this direction, correct? Symmetrically downwards it will be. That magnitude also will be dB because length I'm taking same, current, everything is same only, right? Distance is also same. So this also, if I resolve into the two components, what will happen? This will be dB sin theta. This will be dB cos theta. And very clearly what will happen? This dB sin theta and this dB sin theta cancels because they are in the equal and opposite. They are equal and opposite, so they will cancel. The net magnetic field due to these two, it will come what? dB cos theta plus dB cos theta. But at the same time, you need to keep in mind like this. If I consider any two diametrically opposite sections of this, if you are taking whose length is dl, if you take, their sine components cancel off, and this cos components actually add to the net field at the point P. So the net magnetic field at the point P, if you are going to get it will be nothing but what you have to integrate all this or just add together, addition, right? Summation dB cos theta, we can actually write, correct? So what will that be equal to summation? What is dB? We have already found mu naught by 4 pi, right? IDL divided by r square plus x square, correct? And cos theta, if you are taking cos theta is what? Adjacent by hypotenuse. What is adjacent? It is nothing but r divided by r. Very clear. Now here, other than DL, everything you can take it outside the summation because only DL will be part of this summation. So you'll be getting mu naught by 4 pi into I divided by this R is nothing but root over. So let's write it as R square plus X square into R divided by this is root over R square plus X square, which you can write R square plus X square whole to the power half. Correct? Right? Into summation DL also will become. So this will be equal to what? Mu naught by 4 pi I R divided by C to the power 1 to the power half means you can write it as R square plus X square whole to the power 3 by 2 you can write. Into summation DL is what the total length of this, correct? Summation DL, you can write it as the total length of that circular loop, which will be nothing but 2 pi R. So this will become 2 pi R. Correct. Pi cancels. This 2 and 4 cancel 2. And R into R, you'll be getting I R square. So you'll be getting what? Mu naught I R square divided by 2 into R square plus X square whole to the power 3 by 2. And this is the magnetic field at the point P due to the circular current carrying coil. How much is that? Mu naught I R square divided by 2 into R square plus X square whole to the power 3 by 2. And that's the relation that we want here. Let's go for the next question. The series LCR circuit. We are going to derive expression for its impedance and the phase difference between current and voltage. So what is series LCR circuit? Here we are having the inductor, right? L, a capacitor and a resistor. Here we are having, right? They are connected in series. This is connected across an AC source. Okay. This is L, C, and R. L is the self-inductance of this uh, inductor. C is the capacitance of the capacitor. R is the resistance of that resistor. Okay, they are connected in series to an AC source. Okay, so in this case, what you have to do, first you take the current across the current, let's take it as I naught sine omega t, suppose. Okay, then we'll find the current, the voltage. That's what we are going to do. That will be the easiest approach for this because in series, what will happen? The current across each element will be same, right? So the peak value of voltage, if you are taking across the inductor, what will that be equal to? The peak value of current into the inductive reactance. You can actually write I naught into XL. We can actually write here, correct? The same way, the peak value of voltage across the capacitor, if you are taking it, will be nothing but what I naught into XC. We can actually write. The peak value voltage across the resistor, we can write it as equal to what? I naught into R, correct? So these, if we are going to draw the phasor diagram here, correct? How will I draw the phasor diagram here, right? See, if I take the voltage across the resistor, if I'm going to take, what would that be? This is the current across, this is the peak value of current, let's say, correct? The peak value of current, and let's mark it as I naught. Now the peak value of resistor is actually, we know it is in phase with that. So V naught R, you can write like this. Now what about the peak value of the voltage phasor across inductor? If you are marking, this is what V naught L it will be coming. Okay. And this is V naught C. Why? Because the voltage across the inductor will lead the current by pi by 2. At the same time, voltage across the capacitor lags behind current by pi by 2. So their voltage phasors we drew. So if we have taken here, suppose let's say V naught L is more than V naught C. That's why we have their relative values. You can see I drew the V naught L phasor more bigger, correct? So obviously the resultant voltage phasor, if you want to find, this is how we can do that. This, see, V naught L minus V naught C. This is what it will be, minus V naught C, correct? And the resultant you can find like this, just like how you do parallelogram law of tradition, right? So this is what the resultant you'll be getting, which is nothing but V naught, which leads the current by phi. Correct? Why it is leading the current? Because obviously I've taken V naught L as more than V naught C. So obviously the voltage will lead current by phi. So what are the things that we need to get here? First, we need to find what is the impedance, and then we need to find phi here. That is the phase difference. Phase difference is nothing but phi. Okay, so for this, what we do, we have the peak value voltage in from this triangle that you have got, right? You can write actually V naught. What is that equal to? That is coming as hypotenuse of this, right? So root over what you can write here, uh, base square plus altitude square. So V naught R square plus This is nothing but V naught L minus V naught C the whole square. You can actually write. So now if you substitute the values here, you get a root over I naught, right? I naught R the whole square, right? Plus I naught XL, correct? I naught XL minus I naught XC the whole square it will become, correct? So this I naught you can take it outside. The left hand side also you can write if Z is the impedance. If you mark Z is the impedance of the circuit, then I naught into Z you can write into root over R square plus XL minus XC the whole square you can write. What will happen? I naught cancel. We get the relation for the impedance. What is that equal to? Root over R square plus XL minus XC the whole square. Very clearly we can actually write. This is the relation for what? The impedance that you'll be getting. All right. What is the second part of this? We need to find the phase difference. Very clearly you can do. In this triangle itself, if you are taking tan phi, if you take, what will be tan phi? And the opposite by adjacent. What is opposite? V naught L minus V naught C divided by V naught R. You can actually write. And what will that be equal to? V naught L is nothing but again I naught XL minus I naught XC divided by I naught R. I now, if you take common from the numerator, that will cancel with that in the denominator. You get tan phi. What is that equal to? XL minus XC divided by R. Or the final relation, the phase difference phi, you can write it as what? Tan inverse XL minus XC divided by R. And this is the phase difference relation that you'll be getting. Let's see the mirror equation now. Okay. We are doing this derivation for a concave mirror, right? And we get to the final relation, which is nothing but 1 by, what is the mirror equation? 1 by V plus 1 by U, that is equal to 1 by F, right? This is the relation that we are actually getting over to. So how to do this one? We have to consider a concave mirror. All right, right. The principal focus of this we are marking, and this is the center of curvature. If an object we are placing beyond the center of curvature, that is AB, it forms a real image we know between the center of curvature and the principal focus, a real image. So for that, I'm considering these two uh, rays I'm going to consider because for image formation, at least two rays I need to consider. One is going parallel to the principal axis, falling on the concave mirror. After reflection, it will pass through very clearly through what? The principal focus. A second ray, what I'm going to take, I take it like this second ray actually falls directly onto the pole. So if this ray directly falls onto the pole after reflection, this will pass through similarly onto the other side and the final image will be formed like this. Correct. This is how we'll be getting this. Correct. Let's say this is A dash and B dash. Okay. So where the object distance, obviously, this is what the object distance is. This is the image distance. Correct. This is the principal the focal length. Correct. So how do you relate between these two? Very clearly, one point you need to keep in mind, we are considering only paraxial rays only. Okay, we are not considering any of those marginal rays. The points, this point of incidence, all, suppose if you are taking M, this is very close to the point P you can actually take. So the angles involved will be very small. Okay, that's the basic consideration you'll be taking here. So what we do here, we have to consider the similarity between two sets of triangle. The first set of triangle that I'm going to take is triangle A dash B dash F and triangle FMP. Okay, FMP. Okay. See, actually, the basic consideration you need to keep in mind. See, if I put down a perpendicular from M, this point is N that I'll be taking. Since it is paraxial rays we are considering, this point N will be very close to P. Okay. So if I'm taking suppose MN, okay, MN, you can take it as what? MP only because N and P are very close to each other. You can take it as what? Very small. Okay, Mn, right? So instead of considering the triangle FMN, we are considering the triangle FMP. So now how do you solve this? See, these two triangles, are they similar? You can actually show that they are similar. How do you tell that? See, the angle, if you are taking B dash FA dash, correct? B dash FA dash and angle MFP, they are actually same, correct? These two angles will be same. Why? Because they are opposite angles. Right. At the same time, if you are seeing you have one 90-degree angle also coming, so obviously all the three angles are same. Correct. So maybe by AAA similarity, you can tell that these two triangles are similar. You can actually tell. So if these two triangles are similar, their corresponding sides are in proportion. So you can write what A dash B dash divided by what is the corresponding side of that? It is nothing but MP. Okay. And that is equal to what you can write? We can write it as B dash F divided by FP. We can actually write. Correct. This MP, but what is it equal to? MP is actually equal to, you can see it is equal to AB. So this relation we can write here one relation, which is A dash B dash divided by AB. What is that equal to? B dash F divided by FP. Okay, this is one relation that I'm going to mark here. One more set of triangle that I'm going to take, and we consider that as similar. Okay, we see if they are similar. Triangle, let's say A dash B dash P and triangle ABP. Are they similar? Yes, of course, because angle of incidence equal to angle of reflection. Angle APB and angle A dash PB or B dash, if you are taking, they will be equal. One set of 90-degree angles are coming, and the other two angles also will be equal. So obviously, these two triangles are also similar. So again, for this you can write A dash B dash divided by AB corresponding sides. That will be equal to what? B dash P divided by BP you can write. So when you consider these two equations, equation number one and the two, if you are going to take, what you are going to get here, equation number one and two, if you equate, left hand sides are same. So very clearly you can write B dash F divided by FP. What is that equal to? B dash P divided by BP. Okay. So here you need to see B dash F, we don't know the value. So I'm going to write B dash F. What is that equal to? B dash P minus FP I'm going to write, right? B dash F you can see. B dash F very clearly you can see it is equal to B dash P minus FP very clearly, right? So this equation number, equation 3 actually becomes what? B dash P minus FP, right? B dash P minus FP divided by FP. What is that equal to? B dash P divided by BP. Now, what are these values? Let's like write here with the sign convention we need to write. What is B dash P? B dash P is actually the image distance. So you have to take it as what? Minus V. What is BP? BP is actually equal to minus U, correct? That is the object distance. You have to take it as what? Minus U. What about FP? It is equal to the focal length. I'm taking as what? Minus F. So our equation number 4, what will happen to that? What is B dash P? We have minus V. So minus V minus what is FP? Minus F. So plus F it will be coming divided by FP is again minus F. That is equal to B dash P minus V divided by minus U you have to write. So this become what? V by F minus 1. That is equal to V by U. See here what I'm going to do. This is V. Okay. So here what I'm going to do now. I'm going to divide both the sides by V. So you get 1 by F minus 1 by V. That is equal to 1 by U. All right. So now if I take 1 by U to the right hand side, you get 1 by F is equal to what? 1 by V plus 1 by U. And that is the mirror equation that is required in this. Okay. So that's how we derive mirror equation. The next question, refraction at spherical surface. For this, we consider a, a spherical refracting surface. Let's say here we are having this. On the left side of this, let's say the medium is of refractive index N1. On the right hand side, it is N2. Let's draw a principal axis for this. We consider an object that is placed at a distance U in front of this. A ray of light is falling, okay, from this point object onto this spherical refracting surface. Let's say this is the center of curvature of the spherical refracting surface. So this will be the normal at that point you can actually write, correct? So this will be the angle of incidence you can mark. And this ray will bend towards the normal. Let's say N1, N2 is more than N1. So it will bend towards the normal. And finally, this will bend and meet at the principal axis. Okay, let's say if a ray directly passing through principal axis meet at this point and you get an image at this point. Right? This is how the spherical refracting surface is coming. See here, I want you to mark, see the angle of refraction also you can mark. This is the angle of refraction that will become, correct? Let's mark here three angles. This is alpha, this is beta, and this is gamma. Okay. See, this point is M, where the point of incidence we are considering. And this point is P, which is very close to this point N, right? We are considering only what paraxial rays only we are considering. So this N will be very close to P. So instead of taking Mn, we take it as what? MP only. So now let's see what we do. You consider tan alpha. Since again, marginal, paraxial rays we are considering, angles are very small. So alpha you can approximate, tan alpha you can approximate to alpha. And what will that be equal to? You can write Mn or MP, correct? MP divided by On, we can actually write. All right. At the same time, tan beta, you can approximate to beta. What would that be equal to? MP divided by PC. Correct. At the same way, tan gamma, if you are going to get, what would that be equal to? You can approximate it to gamma. That will be equal to MP divided by, what is this? MP divided by PI. Clear now? So now, if you consider the triangle, let's consider a triangle MOC. Okay. In the triangle MOC, the angle I, if you are taking, that is the exterior angle, and alpha, this alpha and this beta, if you are going to take, it will be the interior opposite angle. So what is the relationship between exterior angle and the interior opposite angle? Exterior angle is equal to sum of interior opposite angle, correct? So you can write very clearly, I is equal to alpha plus beta, you can write. So what is I? Sorry, alpha, we have here, we are having MP divided by ON plus MP divided by PC, you can write. This is I, okay? That you can keep it as I is equal to what? MP divided by ON plus MP by PC. I'm considering one more set of triangle. Which set of triangle we can consider here? MCI. Okay, MCI. In that, again, interior and exterior angles if you are taking. Which is the exterior angle here? Beta is the exterior angle. R and gamma are the interior opposite angle. So you can write the beta, that is equal to what? R plus gamma. Or R is equal to what? Beta minus gamma, you can write. And that will be equal to what? What is beta? We have MP divided by PC minus MP divided by PI. Very clear now. So now we apply what? Snell's law. Okay. We apply Snell's law where Snell's law at M. If you apply Snell's law at M, what is that we are going to get? What is that Snell's law? Snell's law is nothing but what? Sin I by sin R. Correct. That is equal to what? Refractive index of second medium by refractive index of first medium. Again, we apply the small angle approximation. Sin I, you can approximate to I. Sin R, we can approximate to what? R. So this will be giving you I by R, that is equal to N2 by N1, or N1 I, that is equal to N2 R. Now we have the relation for I and R here, right? This is I and this is R. So we'll substitute that values here. So N1 into MP divided by I is nothing but what? NP divided by ON plus MP divided by PC. What is that equal to? N2 into MP divided by PC minus MP divided by PI. You need to keep in mind this MP that is common, we'll take it outside and it will get cancelled. Okay. And right, and these two terms you can see PC is common, so we need to bring it together. The other terms will bring together. So you get N1 by ON plus N2 by PI. What is that equal to? N2 by PC. This term is also PC only, so N2 minus N1 by PC will be getting. Now, what are these values? ON, all these values. See, ON is actually the object distance you need to mark. This is the object distance. PC is nothing but what? The radius of curvature, and PI is the image distance. So when you're taking ON, you have to take it as what? Minus U, correct? With the sign convention. PC, when you're taking it is R only. And lastly, the pi when you are taking it is v. So this, if you substitute in this, you get n1 by what is ON? It is minus u plus n2 by what is pi? Pi is v. That is equal to n2 minus n1 by r. Or this is our relation that we call it as the NUVR relation or the refraction of spherical relation, surface. What is that? N2 by v minus n1 by u, that is equal to n2 minus n1 by r. This is the relation for the refraction at spherical surface or the NUVR relation. Next question is lens maker's formula. Okay. So for this, what we have to do, we have to consider a convex lens we are seeing. See, a convex lens, let's say, right? Let's say the radius of curvatures of both the sides are R1 and R2. Okay. R1 and R2. Let's say the surrounding medium is of refractive index N1. The lens is of refractive index N2. Let's draw the principal axis of this. A point object you are placing in front of this. How actually the real refraction actually take place inside the lens? See, a ray of light falls onto the lens, right? See, here is very, very importantly, you need to consider. The first refraction takes place here, right? And the ray that has been refracted by the first surface actually falls onto the second surface. If the second surface was not there, the image formed by the first surface might have been formed here. This we are going to mark it as suppose I dash. But this image I dash that is formed by the first surface is falling on the second surface, which will get refracted again, and a final image is formed I. Okay, let's say the object distance is u. Okay, the image formed by the first surface we mark it as the image distance. Let's mark it as v dash, and the final image distance we mark it as what v. All right. So if you are considering the refraction at the surface, let's mark this as A, B, C, and this is A, D, C. So we consider the refraction at A, B, C if you are considering. We already know the NUVR relation or the refraction at spherical surface. What is that? N2 by V minus N1 by U, that is equal to N2 minus N1 by R. So this, if you are going to apply for the surface ABC, what you are going to get? Second medium is obviously N2 only, divided by image distance is what V dash minus first medium is N1 by object distance is U. That is equal to N2 minus N1 divided by what? R1. This is our first equation. Hmm. Now, the same thing we do in the case of refraction at the spherical surface ADC also, correct? Which is actually what you need to keep in mind. The object for the second surface is the image formed by the first surface, which is I dash, correct? So when you are writing the relation for this, the second medium is the having the refractive index what N1. Keep that in mind. So N1 by final image distance, what it is V minus first medium is of refractive index N2 divided by the image distance is what V dash. Okay, that is equal to what N1 minus N2 it will be coming divided by R2. Correct. This is the second equation. I hope you got this. Divided by R2. Okay. So what we have to do now, these two equations, the first and second equation, you just add together. So what will happen? This N2 by V dash you can see on the left hand side in both the terms, 1 and 2, you can see it is opposite, right? N2 by V dash minus N2 by V dash. It will cancel off. You get N1 by V minus N1 by U, that is equal to, you can see here, N2 minus N1, if I take common outside, 1 by R1. In the second term, N1 minus N2 it was, so you need to reverse it. So 1 minus will be coming, right? So that will be minus 1 by R2. You'll be getting very clearly. Now this N1 that is there on the left hand side, you take common outside, take it to the right hand side, you get 1 by V minus 1 by U, that is equal to N2 by N1 minus 1. N1 by N1 is 1 into 1 by R1 minus 1 by R2. Or you get 1 by V minus 1 by U, that is equal to, what is it? N2 by N1 is N21 minus 1 into 1 by R1 minus 1 by R2. Okay, we know this very clearly. If you have a convex lens, if the object is at infinity, right, where the image will be formed, the image will be formed at the principal focus, right? If the object is at infinity, If the object is at infinity, image will be formed at what the principal focus. So our equation, the left-hand side, if you are taking, we apply this in that. You get what? 1 by v minus 1 by u. You can write it as what? 1 by f minus 1 by infinity, which is equal to 1 by f. Okay, so this, if I substitute back in our equation here, you get the final result here. What is that? 1 by f, that is equal to n21 minus 1 into 1 by r1 minus 1 by r2. And this is the relation that is required here, which is what we call it as the lens maker's formula. What is that? 1 by f, that is equal to what? N21 minus 1 into 1 by r1 minus 1 by r2, where r1 and r2 are the radius of curvatures of both the surfaces. N21 is n2 by n1, which is the refractive index of second medium with respect to first medium. Here we go for the next question, the refractive index of material of prism. We are going to derive an expression for it. Okay. So let's consider here the prism. Okay. See, yeah, here we are having the prism. Let's say A, B, C. AB and AC, let's say they are the refracting surfaces, and you have BC as the base. A ray of light is incident here, let's say, right? So here I'm drawing the normal at that point, and this ray will pass through. Here also I'm drawing the normal. Let's say these two normals are meeting at this point, and this is the emergent ray. PQ is the incident ray, QR is the ray that is traveling inside, and RS is the emergent ray. The incident angle of incidence is I, we are marking. The angle with which the ray is emerging out, we are marking angle of emergence. This angle, let's mark it as R1, okay, refraction angle. This is R2, right? If I extend this incident ray, right, and if I extend this backward, this emergent ray, they meet together at this point. Okay, let's mark that point as M, and this below point, let's mark it as N. And this angle that is there between the direction of incident ray and the direction of emergent ray is what we call it as what? Angle of deviation. Because the light ray, you can see it was coming like this, right? Now it got deviated, right? So now it is going like this. So the deviation, you can mark it as what? Delta. Delta is the deviation here, right? So now if two angles, if I'm going to mark, which two angles I'm going to mark? This angle, okay? How much will this angle be? This angle, if you are taking, it will be these, you can write it very clearly, it is I minus R1. Same way, this angle, if you are going to mark, it will be E minus R2, you can write. Clear? So now, if you consider the triangle QMR, suppose, okay, or you consider the quadrilateral, okay, the quadrilateral AQNR. In triangle, the quadrilateral AQNR, what you can tell basically, this, since these two angles, if you are taking AQN and angle ARN, they are both perpendicular, correct? Because 90 degrees, they are the normals. QN and NR are the normals. So those two angles, if you take, it will be 90 degree. So very clearly you can write the A, the angle of prism plus angle QNR, correct? QNR. What is that equal to? That will be equal to 180 degree. Very clear, correct? Because the other two angles, sum will be 180 degree. Total in a quadrilateral will be 360 degree. So A plus angle QNR will be 180 degree. At the same time, you consider a triangle, which a triangle QNR. Okay. In triangle QNR, if I'm marking R1 plus R2 plus angle QNR, what will that be? This will also be 180 degree. Sum of three angles in a triangle is 180 degree. So if I consider these two equations, equation number 1 and 2, what you can tell basically, yeah, equation number 1 and 2, if you are taking, what we can take, see, QNR is coming common, right, in both the equations. Right hand side also same. So very clearly you can write A is equal to what? R1 plus R2, correct? So this is one relation that we can use in this. Equation number 3, I'm going to mark here. At the same time, if you consider now triangle, which triangle we can take? We can take MQR, triangle MQR. Again, we go for exterior angle and interior opposite angle. What is the relation? Exterior angle is equal to sum of interior opposite angle. So, which is the exterior angle here? That is the angle of deviation delta. And which are the two interior opposite angles? this I minus R1 and E minus R2. So delta you can write it as equal to what? I minus R1 plus E minus R2. Or that is I plus E minus if you take common R1 plus R2 we can write. What is R1 plus R2 from equation number 3? I plus E minus A. Delta we can actually write, that is equation number 4. Okay. So now in this case, you see, we need to consider the relationship between the angle of incidence and deviation. For small angle of incidence, the angle of deviation will be large. And now if angle of incidence increases, angle of deviation decreases. Okay, for one particular value of angle of incidence, which is that value, it is nothing but at that point, angle of emergence will be equal to angle of incidence. The angle of deviation will be minimum. Beyond that, if angle of incidence increases, angle of deviation also increases. Okay, so if I is equal to E, R1 will also be equal to what? R2. Let's write it as R also. This is at when delta is equal to what? dm. So at delta equal to dm, what will happen to equation number 3? Equation number 3 become A is equal to R1 plus R2 or R plus R, which is 2R. Correct? This will give you what? This will give you R is equal to what? A by 2. It will be giving you very clearly. Correct? This, let's say this is equation number 5. Now, at the same time, what will happen to equation number 4? Equation number 4 becomes I and E both are same. So, delta is nothing but dm. dm is nothing but what? 2I minus A. Or if I'm finding I here, you get what? A plus dm by 2 you get. This is equation number 6. Now, very clearly, if I apply Snell's law, okay, at any both the points, if you want, you can apply. But I'm applying at a point at Q, let's say. So what is that we'll be getting? Sin I by sin R. What is that equal to? It is nothing but what? Refractive index of the lens. Okay, if you take suppose the surrounding is air, by the first medium is 1 only. Refractive index will be 1 only. So you can write n is equal to what? Sin I from equation number 6. What is that we are having? A plus dm by 2. Correct? Divided by sin, what is R? A by 2. And this is the required relation here for the refractive index, okay, of the material of prism in terms of the angle of prism and the angle of minimum deviation, where n is equal to what? Sin A plus dm by 2 divided by sin A by 2. Let's see the theory of interference next. Okay, what is theory of interference? If two waves suppose are meeting together at point, the resultant displacement, what it will be? This is basically given by the principle of superposition. What is it? The resultant displacement will be what? The vector sum of displacements due to individual waves, correct? So if let's say the displacement due to the first wave, okay, we have two waves that are meeting together at a point, correct? So the displacement due to the first wave, let's write it as A1 sine omega t, okay? And let's say the second wave, displacement due to that relation is A2 sine omega t plus phi, right? This is the second. So if I'm finding the resultant displacement, what would that be? By principle of superposition, it is y1 plus y2, very clearly. So this will be equal to what? A1 sine omega t plus A2 sine omega t plus phi. All right. So now you see here what I'm going to do. I'm going to apply this identity. What is that? Sine of A plus B. What is that? Sine A cos B plus cos A sine B. So you get this A1 sine omega t plus A2 into what is this equal to? This is sine of A plus B, which is sine A cos B. So you'll be getting sine omega t cos phi plus cos omega t sine phi. All right. So this you can write it as A1 sine omega t plus A2 sine omega t cos phi plus A2 cos omega t sine phi, we can write. Okay. Or I'm rewriting this as A1 sine omega t plus A2 cos phi, right? A2 cos phi into sine omega t plus uh, A2 sine phi cos omega t, correct? Sine phi cos omega t. So here in the first two terms you can see sine omega t is common. So you do one thing, you can write A1 plus A2 cos phi into sine omega t plus plus here what will happen here? This is A2 sine phi cos omega t or A2, yeah, A2 sine phi cos omega t. All right. Yeah, it's coming behind me, but yeah, you can, I hope you got this. So now you see here what I'm going to do. See, we'll do one thing. This first term that I've written in bracket, which is A1 plus A2 cos phi. Okay, A1 plus A2 cos phi. Let's write it as equal to A uh, A cos theta. Okay, and A2 sine phi. Let's write it as equal to A sine theta. Okay, so what will happen to our relation here? This equation actually becomes y that is equal to A cos theta into sine omega t, correct? Plus A sine theta into cos omega t. Okay, if you take A common outside and rearrange this thing, you get what? Sine omega t cos theta plus cos omega t sine theta. Okay, we get it back again. Okay, sine of A plus B, sine A cos B plus cos A sine B. So this you can write it as what? Sine of omega t plus theta you will get. So you see the resultant displacement here is that here is what we are getting. Y is equal to what? A sine omega t plus theta, where A we call it as the resultant amplitude. And what is the resultant amplitude we'll be getting? From these two equations, if suppose let's say this is equation number one and this is equation number two. Okay, you square and add these two equations, you'll be getting the resultant amplitude. Okay, and what would that be? See, right hand side, if you square and add a square cos square theta plus a square sine square theta, you get just a square because cos square theta plus sine square theta is 1, and that will be equal to what? Left hand side also you need to square and add in this case, right? So what is that you'll be getting? You'll be getting a1 square plus a2 square cos square 5 plus, see, a plus b whole square, that's what you'll be applying. So 2a1 a2 cos 5 plus the second term also it will be coming a2 square sine square 5. Okay, in these two terms you can see a2 square taking common outside, you'll be getting cos square 5 plus sine square 5, which will be 1. Finally, you'll get a is equal to what? Root over a1 square plus a2 square plus 2a1 a2 cos 5. This is what the resultant amplitude you will be getting here. At the same time, if you want the resultant phase difference also you can write. You find the ratio of this thing, you'll be getting theta that is equal to what? Tan inverse. Sine theta by cos theta is tan theta. So tan inverse of A2 sine phi, correct? A2 sine phi divided by A1 plus A2 cos phi. Like this, you can write the theta also. Now, when it comes to the case of the resultant amplitude, two conditions also we can actually write in this case, right? When cos phi is equal to 1, if you are going to take, okay, what will be happening here? You get A is equal to root over A1 square plus A2 square plus 2A1 A2, which is nothing but A1 plus A2, the whole square root, which is nothing but what? A1 plus A2. Okay, and this is condition is what we call it as what? The constructive interference you can call this. And when is this possible? When phi is actually even multiples of what? Uh, pi that you'll be getting. So that is equal to 0, 2 pi, 4 pi, etc. If you are going to take, okay, you'll be getting A is equal to the resultant amplitude will be maximum, and that's what we call it as constructive interference. Now, when you're taking cos phi is equal to minus 1, this if it become minus 1, okay, what will happen? The resultant amplitude will be equal to A1 minus A2, the whole square root will come, which is A1 minus A2. This condition is what we call it as the destructive interference, where one wave actually destroy the other. This will be like when the first wave is actually in the is in out of phase with the second wave, or the crest of one wave is superimposing with the trough of another wave. This is possible when phase difference is actually the odd multiples of pi. So pi, 3 pi, 5 pi, etc. When it is coming, what will be happening? Cos phi will be equal to -1 you'll be getting, and the resultant amplitude will be minimum. And this is what we call it as the destructive interference. Okay, and this is what generally we call it as what the theory of interference. Quickly, we'll discuss this question also, the halfway rectifier. Okay, majority it is coming actually the theoretical part, but quickly we'll discuss how actually the theory is. Okay, so in halfway rectifier, what is that we are having? We have an input source, right? Input AC source. This is connected across the primary of a transformer. And here you have the secondary of the transformer where this is connected to just a single diode. Okay. And you have this is the output resistor across you will be taking the output. Okay. The load resistance across which you will take the output. Here is the input you will be getting, right? The input AC wave that will be applied, right? So here, if you are marking the input waveform, how it will be, input waveform is like this that you are marking, correct? Let's say this is how the input waveform, randomly I'm drawing this, right? This is the input waveform, the different positive and negative half cycles. This is the input cycle, right? That will be marked. So, right. So, what will happen here in this case? During the positive half cycle, if you are taking these 2 points A and B in the secondary of the transformer, if you are seeing during the positive half cycle, what will happen? The point A will be positive, B will be negative. Diode D will be forward bias, correct? Because if this is positive and negative, what will happen during the during the positive half cycle? What will happen? Diode will be forward bias and it conducts current, and current will flow across the load resistance. So you'll be getting output during the positive half cycle. During the negative half cycle, but on the contrary, what will be happening during the negative half cycle? During the negative half cycle, what will happen? A will be negative, B will be positive. So it will be reverse bias. It will not conduct current. So no current across the output will be coming. So what is the point here? The only during the positive half cycles you will be getting the output. Okay, so this is why we call this as basically a halfway rectifier. Okay, what does a rectifier do? Rectifier actually converts AC to DC, correct? So here, has the AC been converted to DC? Yes, the AC has been converted to DC. Why? Because current is only flowing in one direction across the load resistance. Even though it is varying, it is a pulsating DC, you can tell that current is flowing across the load resistance in one direction, and the rectification process has been achieved here in this case. Okay, through the load resistance, current is flowing only through one direction. Only the during the positive off cycles, current will be flowing. Okay, that is why we call this as the half wave rectifier. But now, if you see the case of full wave rectifier, what difference it is? In the case of full wave rectifier, you be having two diodes instead of one diode. And how is the input and output cycle of this? The transformer, the primary and the secondary of the transformer, this is how it will be. This is the input AC you're applying to the primary of the transformer. Right here we have the secondary of the transformer. In this case, note that we'll be using two diodes. Okay, and a special mechanism that we call it as the center tap mechanism we are applying, across which we'll apply the load resistance, okay, across which we'll take the output. Now, what difference is it from halfway rectifier? If this is the input cycle of this, if you are seeing, okay, how will be the output of this? Let's see. Yeah, all right. So this is the input waveform that we are seeing, input current or voltage, like this you can mark. The output waveform, how it will be. Now, during the positive off cycle, as we have seen, what will happen? The point A will be positive and the B will be negative. So, what will happen? The diode D1 that I'm marking here will be forward bias, but the diode D2 will be reverse bias. So, what will happen? Through the second part of this, through this branch where there is diode D2, current will not flow. The current will flow only like this, right? Through the top loop, only the current will be flowing. Okay, you'll be getting the output across the load resistance. So there is output across the load resistance. During the negative off cycle, what will be happening? B will be negative, but B will be positive, A will be negative. Current will flow like this. But in that case, you have to note what diode D2, then it is forward bias because P side is connected to the positive the higher potential, right? So D2 is forward bias, D1 is reverse bias. So what will happen? D1 does not conduct current, D2 will conduct current. Now how will it conduct current? Like this, like this. Okay, so during the negative half cycle also you will be getting the output across the load resistance. And very importantly, you need to note that during both the positive and negative half cycles, the output current is actually flowing through the load resistance in the same direction only. Okay, it is very clear, evidently seen in this case. So during the negative half cycle also, what will be happening? You will be getting output. Okay, and very notably, the thing is current is flowing through the same direction across the load resistance. So again, this will continue during the positive half cycle and negative half cycle. What we'll be getting is a pulsating DC, right? So here, both the half cycles, both the positive and negative half cycles are rectified in this case. So because of this, we call this as what? The full wave rectifier. So these are the important questions that are very important actually for the PU board uh, papers. So I hope all the questions are clear for you all. Okay, best of luck for your preparation. All the best for your exams.